So, all right, so now let's change it a little bit. Okay, so now, okay, suppose the goal is slightly modified. Instead of going to 0, we want it to go to some arbitrary xd. Okay, goal is to come to rest at xd. Okay, so again here, coming to rest means the velocity and acceleration at xd should be 0. Okay. We want that. Okay, so in this case, very straightforward modification. So just change your, sorry, it's not tau, it's f. Just change your f to be the following form. Kp, I'm going to get rid of the minus, but I'm going to put an xd minus x here, okay, plus kd xd dot minus x dot. Okay. So actually, this is going to be coming up a lot. Let me call this E for error. Okay, so I'm going to define this to be E. Okay, so now if I rewrite the equation, okay. So we get m x dot plus b x dot plus kx is equal to that, kp e plus kd e dot. Okay. Let me also write this as m e2 dot with a negative in front, okay, because xd2 dot is 0. Okay, and this I'm going to also write as minus b e dot plus kx is equal to this. Okay, and the reason I can do this is xd2 dot equals 0, and also xd dot equals 0. Okay? So let's reorganize this a little bit. So bring the me term over to the other side. We have kx and also the be dot term over to the other side. This is equal to m e2 dot plus, let's see, kd plus b e dot plus k plus k, I think it's just kpe. Okay, so we have that. All right. So this is a little bit different from the equation we had before, right? We had mx2 dot plus this times x dot plus k prime times x equals 0. Now we have a kx over here, right? So we want to ask ourselves, does this do the job? Does this do the job? Okay, so as t goes to infinity, will this get the mass to where I want it to go? Okay, so to answer that question, we look at the steady state solution to this. Okay, so you probably learned from differential equations that when you want the steady state solution, okay, you assume that all the derivatives are 0, okay, because at steady state it reaches some constant value. That's the assumption. Okay, so examine steady state solution. steady state solution x, let's call it XSS. Okay, so how do you do that? Well, as I said, you set the derivatives to 0. Okay, by setting, so E2 dot and E dot equals 0. Okay, so if you do that, you get k times x is equal to kp times E. And remember, E is kp xd minus x. Okay. All right. So I guess you can manipulate this a little bit, clean it up. So let's see, we have k plus kp x is equal to kp xd. Okay, or just all right, so let's see. Oh, we want steady state here. SS. Let's put a SS here. Okay. So we get something like that. So x steady state is equal to kp over k plus kp times xd. Oops. We want this to be xd, right? We don't want it to be something else, but it could be something else. Okay? Now, if xd equals 0, we're okay. Okay? Okay. Otherwise, there's going to be some error. Okay? Otherwise, we have this steady state error, which is not good. Okay, otherwise, E steady state, which is xd minus x steady state, okay, this is non-zero. Okay, and this is not what we want. Okay, so in steady state, this doesn't quite do the job. All right, so the way to fix this, okay, so one fix, and it's a pretty good fix, is to add an integral term. So let me show you how it's done. So keep using tau. F is the same as before. It's kp E plus kd E dot, but now we add one more term, plus ki. Now we add an integral term. So the integral here is E of t dt. Okay. Now, if you add this integral term, put it back into the equations, what we then get is, let's see. I guess, yeah, so it's kx is, it's the same right-hand side, but now we have this term added. Okay, so let's write it down. So m E2 dot plus kd plus b E dot plus kpe, okay, plus this integral term. Let me write it up here. Okay, plus ki integral E of t dt. All right, so This integral is kind of bothersome, right? So what we do is we take the derivatives of both sides. So take d dt, okay, of both sides. Okay, and we're going to get, what do you get? We get kx dot equals m e 3 dot now, third derivative, plus kd plus b e 2 dot plus kp e dot plus, and now if you remember how to take derivatives of this integral term, Leibniz rule, this is just ki times e. Okay? Okay, so in steady state, okay, you can so we set the derivatives to 0 again. Okay. Now, if x dot equals 0, okay, that is, it goes to some constant value. Okay, that is, okay, x becomes some constant. Okay, whatever it may be. Then what do we get? 0 equals 0. Okay, we get e equals 0 as desired. Okay, so this is the idea behind, this is PID control. Okay, so let's go over here. Okay, so what we've just derived is the PID control law. F equals minus plus kp e plus kd e dot plus ki integral e of t dt. Okay, so this is called the proportional term. That's the p, okay, for proportional. Okay, this is the d term. Okay, this is for the derivative. Okay, and this is the integral term. That's the I term. Okay, so this is the PID control law. So if you have a PD control law, that's just the P and D terms without the I. Okay. All right. So this this takes care of the steady state problem. Okay. But nothing's perfect. Okay. There's the no free lunch theorem, right? There's no free lunch in this world. There's a cost associated with this. Okay. And basically, it just takes longer. Okay. So let me now go back to the brief aside that I was talking about before. Okay. So in control engineering, okay, you hear these types of systems are often characterized by something called the step response. Okay. Okay. So let me just illustrate the idea. I don't want to go too much into the details here. Okay. So the basic idea is that suppose our xd, our x desired, as a function of time, is 0 for t less than 0, and at t equals 0, it jumps up to, say, 1. Oops, that's not very good. Okay? So step response characterization. Okay? Then if we use this control law, our x is going to behave, okay, now it depends on how we choose the gains, the kp's and the kd's, right? And the ki's. But typically it's going to look something like, okay, it's going to, if you don't get it just right, it might overshoot a little bit. Okay, and then it'll eventually die down, like so. Okay, so this is our input step. Okay, and this is our step response of the system. And usually, determine whether you've done a good job of choosing Kp and Kd. You look at things like this. You look at, well, how much did I overshoot here? Okay, so overshoot. Okay, and say, how long does it take to settle to within, say, plus minus 2% of the steady state value, right? So this might be the t settling time. Okay, so this might be, say, plus minus 2%, for example. Okay. All right, so that way, or you can plot the error directly. Okay, plot the error, in which case it begins at 1, and it does this, overshoot, and then eventually the oscillations die down, right? Okay, so this is again the overshoot. Settling time would be, say, I don't know, maybe here. Okay, so you'll see descriptions like this used a lot. Sort of input step response, settling times, overshoot, so on. Okay. Now, if you use a PD control versus a PID control, if I can just sort of give you a general graphic illustration. Okay, so if you let's plot the error. So if you use a PD control, what will happen is it'll go down, but you'll get stuck at some steady state error. It's not 0. Okay. So this is what happens if you use PD. Now, if you use a PID control, what will happen is you might overshoot a little bit, but you'll get a steady state error of 0. Okay, so this would be, say, PID. Okay, so it does get to where you want, but it takes quite a bit longer. Okay, so it'll get close, and then from there, the errors have to accumulate, and eventually, you get to where you want. All right. Okay, so that's the mass spring damper system.